Everyone to know this is the best presentation I've been to today. Thank you.
Maintenance, constructability, cost. So lots of different variables. As an engineer, whenever we have an equation and it's got a whole bunch of different variables in it, they actually say it becomes so complicated that it's indeterminate. So you can see that the problem that we have in considering all these different variables, it really becomes a push and pull of those different variables in finding solutions.
Some of our overarching goals for the projects that we get involved related to zoo enclosures is to protect the well-being of the patrons attending the zoo, as well as the animals, while allowing for an intimate, immersive experience. In this industry of zoo enclosures, what's the difference between designing other type of structures is that on other type of buildings and stadiums and all the other infrastructures that we design, there are a lot of very prescriptive codes. The International Building Code, the ASC 7, and many other material standards that we can follow almost like a recipe to determine loading, capacities, and resistance. For an animal enclosure, the resources are somewhat limited. There are some guidance available. The Glass Association of North America, Ghana, has some really good science standards and safety guidelines. We'll share some of those with you later today. There are also some codes of federal regulations for animal treatment, and WASA and AZAF has some ethic guidelines for animal treatment. However, the prescription level that we engineers are comfortable with rules and standards is simply not there, because you can't predict how an animal will react in any given situation. So when you involve someone like JEI that has experience of having seen many glass enclosure projects, we do our best to bridge that gap. Experience does matter. When you bring in an experienced glazing consultant, we have in our toolbox, we have contacts in previous projects that we can retrieve information to bridge that gap, the lack of prescription.
I wanted to add one part of that. You can see the standards and resources we've indicated up there, but of any additional resources where it might give us a lot of information about the animal, the weights of the animals, the size, the velocity they may be able to approach in an enclosure. Those types of things are very important, and to date, we really haven't found many resources associated with those types of information. Any references that you know of? Yeah.
We have a viewing location for lions, but we discovered that sometimes the glass we use is kind of susceptible to scratches.
Yeah.
So it's strong, but you can see scratches. So.
Scratching is a big deal. Yeah.
I would guide you to the AZA husbandry manuals.
Husbandry manuals.
You can go to aza.org and they'll have husbandry manuals on many of the animals. And that'll some basis of like how far they can leap, how much they weigh, all that.
We've been asking architects forever, and they don't know that.
Yeah. Here's the process. So you can start with just Googling what the animal weight is and speed maximum.
Yep.
And then you go from there, and it's negotiating process. So we talk to the animal husbandry team on the project, and we determine, basically using their knowledge, what the animal will actually run at, what speed it will run at. The weight is not negotiable, but the animal is a compressive object. They're soft.
They deform.
So the stiffness of a rhino.
Yeah.
So the logic is that it will run nose first, but it will never do that for its own protection. So then we, through discussion, arrive at some area of math, which is usually 6 inches by 6.
Good to know. Yeah, that's work along the lines that we
But
will
it is
touch about it a
negotiated.
little bit, but
It
it's.
is negotiated process.
Yeah.
We initiate it, but we always seek the animal experts.
Yeah, no, thank you. That feedback really helps the husbandry location. I think that's a wealth of information. And yeah, these are all negotiable variables. Sometimes
Yes.
ownership,
Yeah.
and architects. And
But after the negotiation, it has to be recorded. It becomes
Yes.
part of the project documentation.
Part of the design documentation.
The specifications.
For legal and insurance purpose.
Yeah, and we'll touch on that too. Who takes the ownership of those specifications, which is part of the negotiation. As we were speaking, the number one variable that we have to play with is the characteristics of the animal, right? The weight, the size, and the speed of the animal all play a big role. Later down in the presentation, we will share one of the equations that we use for dynamic impact loading, and you'll see that every single one of these factors plays a role in the impact force. The weight and the size, they're more determined, they're more finite as far as the variability. However, on the speed, where the design with the architect and the landscaping team, there's a lot of possibilities to limit the speed that the animal can attain. There can be variations on the landscaping, and Stuart will touch on that in a little bit, how to prevent the animal from sprinting to the maximum speed that it would attain in the savannah in Africa, and compare that to the enclosure. Here is an example, an excerpt from a project that we were involved in which was a put together set of specifications that outline and detail some of this information that I'm referring to. You could see that many times they provide us with that top speed of a mongoose or a honey badger. But those top speeds, we have to interpret if that is the speed in the wild or the speed that they have calculated to be attainable at the given enclosure.
Yeah, because it says animal speed on land.
Is that in the wild or in the enclosure? Yeah. So you do really need to know your animals. There are unique interactions that the animal can have with enclosure. For example, primates are known to grab anything that they can hold on the enclosure and the habitat and create a projectile hazard. Polar bears, as you've seen in the videos, they thrust against water and they impart immense force in that piece of glass. Big cats can take direct impacts on glass. I was hearing a story, I can't recall who told me this, that one of the bobcats in their enclosure was doing a parkour exercise, and when it hit the glass, a rock was stuck in her paw, and the rock ended up hitting the glass and breaking. And then not only impacts, but on the serviceability part of it, some animals are known to have a taste for the structural silicone that's used to seal the perimeter of the glass. Penguins, for example, we've received reports that they go and pick on the silicone that's surrounding the glass. And if you have an underwater window or viewing area, that can be a big problem because you really don't want to leak in that case. So there's a side of impact forces and the resistance of glass, and there's also the serviceability portion of it that we need to take into account.
Knowing your enclosures and what you're trying to achieve in those enclosures is very important, one of the big variables. Are we doing a temporary holding area versus an open range type of an area where they can pick up a lot of speed? Submerged versus non-submerged types of enclosures? Terrestrial versus aquatic versus aviary? Single species versus multiple species, all that kind of plays into the multiple variables involved in the design of the viewing window area. Knowing the habitat is essentially about understanding the environment, and it will determine the types of structural loads that are caused to the viewing window area. So the animal impact, we've talked about that. There's pedestrian types of loads that people want to be able to stand up against it and lean against it and take pictures of those types of loads. Wind pressures, if it's an external type of a viewing window. Thermal loads associated with it, hydrostatic and seismic sloshing. So whenever you have a pool of water and there's a seismic event, there is a known sloshing force in that seismic event that plays a part of designing that glass or viewing window area. Live loads, floor loads. So sometimes we've actually gotten into very odd viewing situations to where it's viewing from above. Those types of viewing where they're looking down through a glass portal into their environment. So those types of loads can play an impact, and even snow loads. This is a little excerpt of a standard specification. What we'll see, that it must withstand forces including animal impact, human impact, wind forces, seismic forces, thermal movement without failure of the panels. So the structural importance in knowing the materials and the differences between the materials that can be used for viewing windows is critical. And so there's a lot of differences between the main two, glass and acrylic, that will come into play. Glass has a brittle type of a failure, whereas acrylic does not. It's more of a fatigue, ductile type of a failure. And so that plays a difference into it. Tempered glass is typically stronger under static types of loads, meaning that acrylic, you would actually have to have a 2.5 times thickness of the glass to equal the strength of the tempered glass. Glass has less capacity for impact resistance than acrylic because acrylic's more ductile in its failure type and glass is more brittle. Glass is much more scratch resistance. We talked about the scratches. Acrylic mars easily, and glass is non-combustible. Acrylic is combustible. Size considerations associated with glass and acrylic. Glass is typically readily available, monolithic sizes up to 3/4 of an inch. And then beyond that, they have to laminate pieces together to be able to achieve the desired thickness. And so typically you can get those built up to about 3 to 4 inches at most, but that's a very heavy assembly, and it requires a lot of extra planning in being able to get those into place. And also, glass is only available in certain sizes because it has to go through the manufacturing process. Typically 10 to 14 feet in width, and typically length can be a little bit longer than 14 foot, but not much more than that. Acrylic offers size versatility. You can seam it together all day long and you can get great big pieces. It weighs a lot less, and so it's a lot easier to be able to deal with in the setting and getting those into place. Optical quality and glass versus acrylic is a huge factor. So acrylic is superior to glass in optical quality. That's an interesting thing. I really didn't understand that, know that until I did a lot of research, but it's colorless at any thickness. Whereas glass, you've got some stuff inside of the glass, a little bit of iron that you can't quite get rid of, even in Starfire glass, and so there's a difference in the optical clarity of glass at certain thicknesses. You can get low iron glass, you get rid of the green, you get that Starfire for the best clarity of the glass, and that's good. Acrylic will yellow under time, under UV exposure. But for the most part, if you have an interior, you don't have to really get too worried about the yellowing of those types of windows. Acrylic has less distortion than glass underwater. So there's an index of refraction and it's closer to the water, so it makes things appear more normal than glass. Glass will actually magnify because the refraction that's in the glass. Yes.
Something to add about that on the acrylic too. Acrylic absorbs water, so that's what helps with that.
It absorbs water.
Yeah.
And so so it becomes more like the water as it goes along.
And I just find it
Great
doesn't
thing.
hurt it. It has that first little bit of layers, absorbs that water, so that's why you get that kind of clarity.
Nice.
Thanks for that.
Yeah. Thermal considerations, differences between glass and acrylic. Acrylic is 4 to 5 times better insulator than glass is. And so sometimes we have the desire for insulated glass units to achieve a thermal barrier in the area too. But really, whenever we start considering impact and that outboard layup that's required for impact, sometimes that doesn't become feasible to do with insulated glass. And that's one of the considerations that you need to take into account. Acrylic has more solar heat gain. Typically, there's no coatings to be able to reduce those types of heat gains, whereas with glass, you do have the capability of being able to add in those types of coatings, low E coatings and other coatings that will be able to reduce the interior heat gain. Acrylic has significant more thermal expansion than glass does, and so that needs to be accounted for in the supports and the framework for supporting those types of viewing windows.
Diving a little bit deeper into the glass itself, a little bit of background information about the general structural design of glass. When float tempered glass exits the float machine, the consensus is to use an average strength of 24,000 psi. That is the strength at which that new piece of glass would break if tested to failure. The strength of glass does vary by imperfections. As time goes by, we apply certain factors, reduction factors, to account for the weathering of the glass, any UV radiation that degrades the quality of the glass. And there's also a number of other things that are applied to the glass, like ceramic etching and frick patterns, that are there for aesthetic reasons, to conceal parts of the enclosure, for architectural purposes. Those can have an impact on the strength of glass. Bird-friendly applications can also have an impact on the strength of glass. However, there are new technologies now that implement the bird-friendly sticker, if you want to call it for lack of a better term, into the laminate in the glass. And that really doesn't have much impact on the strength of glass. As I said before, the 24,000 psi is a statistical, like if you look at it as a bell curve, the 24,000 psi is kind of like the mean average of strength of the glass. However, for applications on facade, for curtain wall storefront application, the industry allows a probability of breakage of 8 in 1,000. Meaning if your building has 1,000 windows in its facade, there probabilistically we can allow up to 8 of those 1,000s to break for any of those imperfections. Because again, as good as the manufacturing processes have become, glass does carry some inherent imperfections in it. Whenever glass is used in life safety or fall hazard application, we apply a factor of safety of 4 to that 24,000 psi. Meaning that when we run our analysis of a glass handrail, for example, on the 25th story building in Miami, and we are looking at that glass, we're only going to allow that glass to be stressed up to 6,000 psi. That is something that when we communicate with our clients, it's tricky to say, yeah, your glass is failing. That doesn't necessarily mean that it's going to fall and break down. It means that you're pushing your glass to a higher stress that will reduce your factor of safety closer to the 24,000 psi. So that's how the factor of safety gets used in our industry for the design of life safety and fall hazard applications.
In addition to that, I just wanted to make a point that whenever we use a factor of safety of 4 in our design off of the 24,000, gets you down to 6,000 psi, that becomes a probability of less than 1 in 1,000 breakage, much less than 1.
Yeah, and if you think about the 8 per 1,000, no building owner will be happy if they see their brand new curtain wall with 1 light broken. It's a bad day. But the risk of somebody getting hurt from it is very low. Whereas on this case, where we have a full guardrail application, we really want to take extreme measures from preventing a situation like that. And that gets highlighted even more when you have a gorilla behind the glass. And as I said before, there's no prescriptive building code that tells us engineers you need to apply a safety factor of X. The Ghana glazing manual does provide some guideline, and this is an excerpt of that section of the code in which they recommend for animal enclosures, if you're having a fully tempered glass layout of laminates, to use a range of between 2,400 and 6,000 psi as your absolute maximum threshold of stress. And if you remember from the previous slide, a 6,000 psi threshold means a safety factor of 4, whereas a 2,400 psi threshold represents a safety factor of 10. So all of this information meets our responsibility as engineers, as consultants for the glass portion, is to communicate this to the owner, to the architect, to the GC, fabricator, to all the parties involved, so that they can weigh the risk versus cost of this very important piece of enclosure and come up with a desirable performance level.
Yeah. One of the things that I'll add about the safety factor of 10, getting down to this low of a stress reduces probability of breakage way down there, and is typically used whenever we have a life-threatening situation like retaining water back from the patrons. And so that's whenever that typically will get used.
And naturally, safety factor of 10, limiting your glass to no more than 2400 PSI will typically result in very thin pieces of glass, because that's what it takes to redistribute the stress and limit your glass stress to that level. And in the side of construction and safety for glass, of course, size matters. The smaller the viewing area, the higher the resistance for impact. Very intuitive. If you have a 2x2, a 4 square foot window, and you put your hand on it, that thing is rock solid. It won't wobble at all. Whereas if you have a 10 foot by 20 foot piece of glass and nobody did the math on it and they installed a 1/2 inch piece of glass, you can touch it with your finger and it's going to move like a pool noodle. It's going to wobble all over around. So size does matter for the resistance of the impact. And most importantly, I would say, in my experience designing glass enclosures and all types of glass, the support of the glass, it's truly what drives some of the stress risers in the unit. And we'll share a couple of models here in a little bit, and it'll become more clear. But units that are typically supported at head and sill only, that they don't have any vertical supports, any vertical mullions, will typically require to be a lot thicker because they're only being supported on the head and sill. So you have a simply supported slab, basically, that has to distribute the stress and the load only at 2 locations. Base shoes on guardrail applications, they do a lot better job distributing the stress of the glass compared to, say, when you have point supported glass with spider fittings. On those cases, the stress concentration near the holes of the glass sometimes skyrockets, and that sometimes drives the thickness of the glass, not necessarily where the load gets applied, but on those support locations. Beyond these items that have a big impact on how stress gets distributed, I do want to touch base a little bit about the safety and the process that we go through in assuming that a ply will break and what happens after that, the first ply breaks. In the event, and as you've seen in many of the recent videos from the San Diego Zoo and similarly, we take the approach, the industry takes the approach of assuming almost like a sacrificial light. So we design the sandwich of glasses to sustain a load and not to be stressed over 6,000 PSI, 2,400 PSI. But in the case that that first ply cracks, it will shatter and the unit will remain in place. At that point, we still need to account for hydrostatic loadings from the water, any wind loads that might happen, any additional impacts of the animal after that point. But the premise is that we're going to lower the safety factor, because when that happens, the crew, the maintenance, they're going to be made aware, patrons are going to be able to be evacuated from the area, the animal is going to be able to be contained, and corrective measures can happen. So it's pointless to keep that safety factor of 10 after the first ply has broken, because we hope that the maintenance would step in and be like, okay, everybody evacuate the place, we need to fix this. Like I said, those low safety factors are reduced substantially in those situations. And I will say that where we draw a hard line and what should absolutely never happen is a catastrophic collapse of the glass that would come off of the framing, and then you have shattered glass and there's simply nothing between the animals and the patrons. That is a line that we simply stay very far away from, and that is the concept behind the single ply breakage, to allow some flexibility and some time for evacuation. As I said before, this is a picture of a finite element model, and we use a software called SJMetla, which is one of the most common softwares out there for glass and other type of plate analysis. As I was mentioning before, typically we have a rectangular viewing area, and you can have a 4-sided support in which you have a mullion and steel angle supporting the edge of the units. You can have a 3-sided support, and if you think about this and rotate it, you would have a little like balcony area in which you have supports along the jambs and the sill. And a very popular alternative for most architects is having a head and sill support only with silicone butt joints on each side.
Just a quick question. Of these three, Which is the weakest? Last one. Yeah, it is, because if you only have two sides supported, that is the weaker situation.
Because it's only supported at the top of the head and sill, we have to account for the critical location of the load. We have to assume that the animal will impact the glass at a location that it will create the highest stress. And in a condition that you have head and sill anchorage with silicone butt joints on each side, we have to assume that the animal is going to impact the glass somewhere in this location. As you can see in our model here, you have the impact load located on the edge of the glass mid-height. We do distribute the load, and this is a contentious topic lately about, okay, do we distribute the load in a 2-foot square area, a 9-foot square area, an inch? It varies. But that's why the communication with the zoologists and the experts becomes so important. And once we apply the load there, we run the analysis, and you can see here on the contour map how the stress risers occur in these locations closer to the load. But as you can tell, even though the deflection, the deflection at the midspan might be high, but that's not necessarily where the stress is the highest. The stress will be the highest closer to the supports where the glass is contained. And Stuart is going to show a few details here in a second that's going to become apparent.
So this is an example of a non-submerged type of a detail for animal viewing enclosure. You can see the glass that's up here sandwiched in between. In this case, it shows 2-ply glass. And you can see there's an inside angle and an outside angle. And so on the inside angle, this would be something that could be removable by bolts into the secondary angle. And that second angle is bolted into the foundation, into the concrete, so that you have the opportunity to be able to change out the glass in case you need to. You can see up here that we have some spacers on the side, we have a setting block, and we have silicone sealant that is tucked into the sides to be able to seal that off.
Oh, and real quick, if you see this, the edge of where the steel angle would end, all this part of the glass is captured, and in our finite element model, we would model that strip with some elastic lines going from there to there, and creating some fixity in our model. You can see the stress riser there represents where that steel edge basically ends, and the glass is wanting to rotate and really lean hard against that steel leg. And so in that vicinity is where we would see the highest concentration of stress.
This is an example of a submerged type of a detail where you have, in this case, 3-ply glass, you got a setting block, it's contained in a rebate of concrete, and typically you'll have a seal on the inside, the patron side, and you'll have a sealant on the water side, on the animal side. And in addition to that, there's an epoxy waterproofing that would typically get applied prior to the installation of the viewing window. And this is another submerged type of a detail, but it has a protection plate that's involved. And so this is in those cases where you have an animal that is inside that may want to eat or destroy the silicone seal. And so you can protect that seal by doing something that's similar to this, where you tuck that seal down inside underneath that steel plate. The plate is bolted into the concrete. You still have the same rebate, the same setting block, and then the same spacers and the silicone seal on the inside, the patron side.
Some of the common challenges that we have when we have like knee walls or concrete foundation walls is the edge distance and the spacing. With concrete bolts, more is not necessarily better. And if you put too many bolts together to try to get more capacity, you end up breaking off the concrete. And CMU, that's a whole different story. Like CMU block, anchoring to it, it is a pain, and we do see a lot of challenges with it. But the edge distance from the concrete to the center of the bolt tends to be regularly what's the driving force between the number and the diameter of the bolt.
Anywhere in between 2.5 inches to 4.
Yeah.
Some of the habitat variables inside the habitat, in enables us to be able to have a better design. Some of those variables might be objects that are placed into the line of travel of the animal as it's approaching the window. Rocks, logs, things like that may be something that is a growth that might be uncomfortable for the animal to be able to approach the glass. And then there's issues of launches and swings. So we never really want to have a launch pad that is directed towards the glass. We definitely want to make sure that those are away from the glass. Swings, we don't want those in the direction of the glass, but away from the glass. In addition to that, you really want to stay away from assisting the animals of having any projectiles. I've seen this so many different times where in facilities they're giving the animals toys and things like that, and chimpanzee comes up to next to the window and has a rock or something, and they're hitting it time after time, and then all of a sudden shatter and they run. We want to make sure that there's nothing that's in the animal exhibit that can break the glass. I saw this before we actually did the design for Hogle Zoo, their polar bear exhibit. Before we did that, we went and we viewed a lot of videos online. We saw this one of a polar bear that was diving down, and he'd get a rock and he'd bring it up to the top and let that rock go. He'd do it again, and then about the third time, that rock straight up against the window, and you saw the two patrons rush out after that. So definitely the stuff that we put in there for them to be able to interact with is an important part of the equation. We really don't want a lot in there for them to be able to use to scrape or break the windows. And so some of the strategies may be to reduce the impact speed of the animal. I mentioned before some of the different things that we can put in front, obstacles, maybe a wire fence or moats, those types of things. Drop-offs that are before the window where they won't go into the drop-off and gain speed. Some of the other considerations, and we talked about sealant protection, saw some of those details, making sure that we understand the animal and what their desires are to be able to deface the sealant. Installation challenges that are some of the considerations. So if you're in a building that's existing and you want to have a retrofit, you definitely have some constraints there, because the heaviness of glass can build up and it can be undoable. They can't get the cranes in that they need to. They might not have the head distance that they need to be able to get the stuff in. Watch out for those types of variables whenever you get into the renovations. Mirrored glass. I saw an interesting aspect of this where we had some areas that were containment for injured lions, and they wanted to make sure that the injured lions had a place that was healthy for them, where they're not stressed or by the viewing patrons, but they still wanted to be able to allow the patrons to be able to see. So that's an option to be able to consider for the animals. So we're going to go into a few case studies, and so one of the first case studies that we're going to bring up is Detroit Zoo, their beaver pool. It's an outdoor exhibit, and so you can see over there the green represents glass. It's a section view of the facility slicing through it, so we can see that this is pretty tall glass. We have about 4 foot of water contained, and then the top part of that glass is unsupported, meaning that there's no structure, there's no steel support or anything like that. It does have a beauty cap. You're going to see that in a picture in a minute. But it makes it a little bit of an interesting design because it's 3-side supported. So we got a support down here, we got a support on the 2 sides at the rock where it's being supported by concrete, and we got the rock boundary around it. And then we also have a piece of glass back there. Doesn't have as much load with the water, but it's just about 1.5 foot worth of water. And you can see the structure that's overhead. You see the beaver dam that's in the background there. And so ultimately what that ended up being was about 12 foot by 6 foot maximum glass pieces, 4-ply, 3/4 inch tempered, because it was not supported on that top edge. And so it's a weaker design if it's not supported on the top edge, but it allows a good view. And so the 4-plies have an inner layer that's SGP inner layer, which is a tougher inner layer to be able to be used, especially in submerged applications. And here's what it looked like at the end. So you can see it's very beautiful. You have a clear view of the beavers, you know, that whenever they come out of the dam, and you see that beauty cap that was on the top edge. Really doesn't decrease the viewing of the patron.
It's mostly to protect the inner layer from like weathering, and it just goes more overnight if somebody or something goes towards it.
The second case study is with Hogle Zoo, Rocky Shores. I mentioned that we did do the design out there, and so this is a really interesting design because the species interact. So we had polar bear, now this is a plan view, so we're looking down on it. We have polar bear pool that's over here, and we have a seal pool that's over on this side. We had a dividing wall that's in the middle, and we had windows that were in that dividing wall. One of the windows was top side, not below the water, and the other viewing window is on the bottom side below the water. And you're gonna see that in just a minute. Here's where the patrons go down to be able to view. This is all underwater. And so this is the area where they would see the seals and how they're interacting, and the polar bears and how they're interacting with the opposite species. Big glass size, 7-foot bays by 13.5-foot tall glass, made up of 4-plies of 3/4-inch tempered glass to hold back the hydrostatic load. The sloshing load from seismic activity was a big part of that. We did use .060 PVB. I think at that time, back in those days, SGP was really just new. And we do have better options now with SGP. SGP does cost a little bit more, but well worth it. It's much stronger in the applications.
In this case, I'm sure it would have allowed reduction of the thickness of the glass.
I think so, yeah.
I'll just add something to that too, as an installer of the glass. We'll really stray away from the PVB for submersion. So, 'cause
Yeah.
we don't want to be attached to that, because it just, SGP is the way to go, is get budget the extra money, because it's extremely worth it.
Great note, and as an additional note, ASI, you did the installation of this
Yeah,
very
we did.
exhibit at the, yeah, big cranes.
Yes.
Yeah.
That was I remember the cranes that was needed, those panels were very heavy.
Monstrous, yeah.
They were monsters, they were pretty close in the last, once you start getting up to that 5,000-pound range, those are very difficult to handle.
Yeah.
Maneuver.
And I think in exposed application, PVB, we've learned to stay away from it altogether. So the application of PVB interlayers, mostly interior, like partition wall type.
Yeah.
SGP's kind of, and do be careful when you're specifying SGP on the specs or buying it. SGP, make sure that you're getting the Centria glass SGP, because SGP's become like a term in the industry, a generic term, but it's the Centria glass.
Yeah, central glass. 8'6" was the water depth on the glass. You can see that here. So this is absolutely beautiful. You can see it, the polar bear is diving down to that lower window, and they can hear the sounds of each other over the wall, and they can potentially see each other. But he's diving down to look and see. The seals are all up there on the deck. They're not worried at all.
Yeah, they're just chilling.
Yeah. They got a ball out there for them to play with.
This is an ongoing project, and I don't believe Judy's here today. We're from the Living Desert Zoo at Palm Desert, California. This is a project that we were called very early on the process, about 3 years ago, and it's still in the design phases. And this shows the importance of involving your specialty consultants and groups as early as possible in your project. As you can see, on a glass enclosure, there's 2 crown jewels. One, of course, is the animal, and the second one is the glass. You want the glass, everything else surrounding the glass. You can put landscaping rug, you can cover it up, you can have a very ugly beam that's required to hold on the glass. You can't hide anything on the glass. The glass has to be the clear jewel of the event center in this case. So we were brought in to do a feasibility study on an iterative process of how thick the glass needed to be for this application. Event center had some pieces of glass that were 10 foot tall and some were even pushing a little bit over 10 foot tall with no vertical support. At one point during the process, and this is why, again, I highlight the importance of bringing in the specialty consultants early enough that we can highlight areas of conflict or concern. The idea was for this event center to gain some sort of LEED certification for energy efficiency. And there was some ideas of making these pieces as an insulated glass unit, which is a pane piece of either a laminated pane on the outboard, argon or airspace in the middle, and then another one, like what you would see in a storefront or curtain wall application. Very quickly we realized how incredibly challenging and costly that would have become. And from a serviceability point of view, how that would have become also very troublesome to keep up if there's any moisture, dirt, or water that comes in and find its way into the air pocket. You would have spent $50,000 per IGU unit that in the first couple of months you'd start seeing it fog up. So it's not only the structural component that we need to raise flags, but also the serviceability of some of these items that there's not really equations that tell us a yay or nay. It's from experience knowing that, yeah, if you have a 10-foot piece of glass that you want it to be insulated glass unit, it could be challenging because these things could deflect quite a bit, right? So that's the experience that we bring in sometimes on the project, and it bridges the gap of the lack of prescription from codes and what we've seen that has worked in the past. In this event center, the animal being enclosed was a group of lions. So part of the ongoing discussion, and I know Tessera is involved in this project, and we've been working alongside with them too. If you go to the next slide, you could see here first of all, this is the equation that after considering every variable, this is the equation that it basically is force equals MA, like the equation that you see printed on t-shirts everywhere. Force equals MA is the genesis, basically, of this force equation. As you can see, the three main components that determine the impact force is the weight of the animal, which we get from research, from zoologists, from the resources that people like you can share with us. The compressibility of the animal, like Marius, you were saying, that when an animal hits the glass, it's going to compress. And that distance of compression is what gives the acceleration, V over D. And that amount of compression varies from animal to animal. And that is perhaps one of the most elusive variables of the equation, because we can't really be testing this. We can't be throwing animals on a piece of glass and seeing how much they compress. But it's from experience that we get, and a rhinoceros is going to be a lot more like bulky and stiff than a weasel, for example. Their horns are very stiff as well. And then the true driver of the force is this variable right here, V, velocity, the speed of the animal. As you can see, that V is squared. So a very small increase in the velocity that the animal can attain will result in a much higher force. On this table here on the right, you could see that, for example, a 500-pound lion running at 10 miles per hour, the impact force is around 400 pounds. We can safely stay under 6,000 PSI with 3 plies of 1/2 inch glass, so 1.5 inches. What you see in most enclosures, 1.5 inches. If the habitat allows the lion to attain full speed and it goes to 50 miles per hour, our impact force goes to 10,000 pounds. It's like stopping an F-150 truck with a 10-foot tall piece of glass. To remain under the 6,000 PSI stress threshold, we would have required 4 plies of 1 inch each, meaning a total makeup of 4 inches, which would be astronomical.
Question for
Please.
you. I worked in aerospace for a while, and they would take, for airplanes and stuff like that, they would literally take chickens and throw them at the glass, right? At different
Oh,
speeds.
where's the data for this?
That lab.
But any type of animal that they would hit, could hit the plane, different size, stuff like that, they would. But they literally use chickens. The one that I was at, they forgot to unthaw them and destroyed everything. Craziest thing I've ever seen in my life. But
Luckily,
seriously.
we don't have to deal with like frozen penguins. They don't fall.
But I'm just curious, because if you had items that, because I know in crash test dummies and different things like that, if there's a way to project the size and weight of something at glass, whether it can be, like I said, artificial, of course.
Yeah.
But if there's a way to do that, they do that in testing, in manufacturing, quite a bit.
Yeah, yeah.
We'd love to partner with people that are interested in getting that into university. We'd love to be the partners in
Yeah,
that.
and typically, how I've seen that play out is on a given project, it is oftentimes way too late to have a testing program. So our zoo, it's wanting to open next summer and to go through the testing programs of, okay, how much would this type of animal compress upon impact? It would be a very valuable thing, but oftentimes budget and time constraints are like the driving forces against that.
I wouldn't think you'd have to do it once.
Yeah, just once.
Yeah.
So yeah, as you can see, these are the variables that play a role in the impact force, but the impact force then plays a role in the thickness of glass that we have to come up with.
With all that considered, you can see that there's so many different variables that are indeterminate. There's a lot of fluctuation about what speed does the animal actually gain? What's acceptable for the weight of the animal that's going to gain that speed? Those types of variables are very interactive with the design of the viewing window. And the viewing window is the crown jewel of what you're trying to achieve in the patron being able to get into the area of the animal. And it's where it all needs to start at, and then you build around that to the structure and then the rest of the stuff that goes on in that environment. That's what you're trying to achieve. So there's lots of things to be able to value and be able to weigh up and down in that process. Any questions for us? We're about 5 minutes away from needing to move on.
Connect with Jeff's experience is zoos in Europe are very frequently encasing the rivets of glass in the rockwork on both sides, exhibit and guest side. And in the US we don't do this as much, but it seems to be more popular now. What is your opinion on this? Does it reduce the free span of the glass? What if the glass breaks? What's your experience with rockwork has to be removed and replaced?
Yeah, that's the variable. They would have to, the glass breaks and needs to be maintained. You have to dig out that area to be able to expose the glass to get it out and then reset everything and come back and repair that environment. In terms of the glass itself, it doesn't make any difference because it's isolated usually from that with spacers, and so that doesn't really affect
And the
design.
maintenance, like Stuart was saying, the maintenance often becomes a big driving force for the decision from ownership. Because we can design this very stiff, robust support around the glass, but if it's all welded, you're gonna have to tear down the exhibit to replace one piece of glass. So that's another part of that we need to take into account is access to maintenance, access to if a ply breaks, for it to make it a little bit more easier for the crew to be able to unscrew the base shoe or unscrew the angles to remove the piece of glass.
And as the guy that has to replace that glass, and I've had to do that a couple of times, it's great when the engineers and the installers are having that conversation with the people that are saying this has to be fully encased. Like it adds tens of thousands of dollars to the replacement cost, because it's going to break at some point, hopefully.
Yeah.
Not very often, but when it does, it's a big pain.
And that's a repeated theme that we're first-time exhibitors, but the people that I've met, a lot of them are talking about breakage of glass. And so that to me points to under-design in the past. And what really needs to be done in the future is considering these variables more importantly. Yeah, you have a question?
I have a question not related to durability, but so you may not be able to speak on it, more about clarity and guest experience. We have some smaller exhibits that are viewing from outdoors to indoor enclosures, and we have a lot of issues with glare. We've experimented with different products that are supposed to be glare resistant glass. Those have actually been worse for us than just.
Really?
laminate.
Joshua, maybe you can share some from your neck of the woods on like acrylic and glass and how to make
There, with glass, there are some films that will work. I don't remember which ones they are, because we try to stay away from films, because in the end, it just turns into another maintenance nightmare.
Right, that's what we've experienced
Yeah.
with the film.
Acrylic doesn't like the films, because the chemicals from the adhesive over time will start to craze the acrylic, which is microfractures. SeaWorld was tired of all the graffiti, and so they, on a bunch of their exhibits down in San Antonio, that's where they tested it out. They put those films, and within probably 8 months, they called us up and said, "Can you come polish the windows, please? We don't like this film." It's turned into more of a hassle. But there's not really much, unfortunately. You can usually, if you angle, when you're designing the exhibit, if you just do a little bit of an angle for the light refraction so that it changes the direction of the glare.
Yeah, we've
that'd
had
be
some
good.
success with that.
Yeah, or lighting, like you can change, like, by shining lights in certain ways, it'll deflect. So that usually lighting is what most aquariums and some of the zoos we work with.
Yeah, we've tried increasing the light inside of the exhibits, but we don't want to go to the point where we're affecting animal welfare, blinding them with these.
Yeah, you don't want to have the blinding lights and stuff.
The reflection is from inside of the enclosed structure or?
No,
outside?
from the outside.
So
yeah.
the solution usually is to put some kind of dark backdrop from which light would not reflect. It could be landscaping, like coniferous
Yeah.
plants
Okay.
that will stay dark and
Reflecting a lot of our walkways onto it.
and or stain the walkways.
Yeah.
I had an interesting observation of one of the angled panels of glass, and surprised me. Its intent was to reflect from above, prevent from reflections. One thing I've noticed is that people are generally used to vertical glass. People see it all the time with storefront windows. It's all vertical. When you tilt it, you create unprecedented sensation of being something unstable, and it actually throws people off more.
Yeah.
The reflection are still mostly,
Yeah.
but you're creating something new for people.
I know Seattle, for instance, has a 26-degree angle on their main one, and it does really create a sense of wonder when you're standing there. It's leaning, but it's not. It's like that.
Where's the reflection coming from?
They adjust things too with lighting. Like they do a really good job with their lighting. But just real quick too, when I touched on about the rock work too. As an installer, if we have to come replace that window, you're instantly adding $15,000 to $20,000 to the replacement to chop away all that rock work, and then also put it back.
And schedule?
And it's schedule impact too, because it'll take a couple, 2, 3 days, 4 days, depending on how thick that rock work was or what it was. So keep that in mind if you're going to cover up that seal. And the risk of putting rock back to damaging the glass. Yeah. Or the seal.
Folks, thank you so much for your time today. We're beyond the.
Just want everyone to know it's the best presentation I've been to today. Thank you.